Did you know that your home is likely packed with dozens, maybe even hundreds, of tiny invisible computers? Ones you never actually see or, think about?
Mm.
And I'm not talking about your phone or your laptop or even your smart speaker. These are silent, tireless workhorses quietly running the show behind the scenes in pretty much everything.
It's an amazing thought, really, isn't it? We interact with them constantly, but we're completely unaware they're even there.
Absolutely. And that's exactly what we're diving into today. The fascinating, often unseen world of microcontrollers.
Right.
We've gone through, well, quite a stack of sources, everything from dense technical PDFs to market analysis reports, basically to bring you the fastest way to really get what these ubiquitous little chips are all about.
Yeah, our mission today is really to pull back the curtain on these mini brains, show you just how powerful and pervasive they've actually become.
Okay, so what can you expect?
Well, we'll unpack what a microcontroller actually is, how it's different from the processor in your PC. Then we'll look at where these chips are hiding, pretty much in plain sight.
Yeah.
Trace their, well, surprising journey from, room-sized machines down to things smaller than a grain of rice.
Wow.
Explore how they got so incredibly small and sheaf, and then, crucially, why they're so critical for everything from your car to, the whole Internet of Things explosion.
All right, let's jump right in then.
Gotcha.
When we say microcontroller, it sounds like, well, a tiny computer, but it's more specific than that, isn't it?
It is, yeah.
What's the fundamental difference from, say, the processor in my laptop?
That's a really critical distinction. So
Yeah.
at its core, a microcontroller, or MCU, as you often see it written, is essentially a complete small computer but on a single integrated circuit.
A single chip.
Exactly. The key phrase is single chip. Unlike, say, the microprocessor in your laptop, which needs separate chips for memory, input, output, all that stuff.
Right.
A microcontroller integrates all of that. You've got the CPU, you've got memory, you've got programmable input-output peripherals all together in one neat little package.
Ah, okay. So it's not just the brain. It's got the memory and all the connections right there with it.
Precisely.
What kind of memory are we talking about that's baked right onto the chip?
You'll typically find what's called program memory. That's where the instructions, the software for the chip lives.
Okay.
Common types include NOR flash. That's a fast, non-volatile storage type. Or sometimes you see one-time programmable read-only memory, OTP-ROM.
Right.
And there's also usually a small amount of RAM just for temporary data storage while the program's actually running. And it's this on-chip integration that makes it so compact and, well, really efficient for its specific jobs.
And that's why we find them in things like washing machines, right?
Right.
Because they're built for dedicated specific tasks, not general computing like my laptop.
Exactly right. Microcontrollers are designed specifically for what we call embedded applications.
Embedded applications. Okay.
Yeah, meaning they're not for browsing the web or running spreadsheets, but for performing very dedicated functions within a larger system. They're highly specialized tools, really optimized for control and automation.
Got it. Now, I've also heard the term system on a chip, or SoC. Is that just another name for a microcontroller, or is it something different?
Good question. Not quite, though they're definitely related. A system on a chip and SoC is a broader category.
Oh.
While an SoC can contain a microcontroller core, it typically integrates much more advanced peripherals on that same single chip. Things like, a powerful graphics processing unit, a GPU, or maybe a Wi-Fi or Bluetooth radio module.
Ah, I see. So it's like a microcontroller plus more bells and whistles.
Kind of, yeah. So a microcontroller is often a more focused, maybe simpler version of an integrated system, really designed for control tasks.
Right.
And what's particularly clever is how some microcontrollers, these are called mixed signal microcontrollers, they even integrate analog components right onto the chip.
Analog components, why is that important?
Well, it allows them to directly interact with the real analog world, like reading a temperature sensor, which gives an analog voltage, or controlling a motor speed smoothly. It bridges that gap between the digital processing inside the chip and physical reality outside.
That makes perfect sense because, yeah, the real world is analog, isn't it? It's not just ones and zeros.
Exactly.
So if these things are so specialized and integrated, and you say they're everywhere, where are they actually hiding? Because I still don't feel like I've ever really seen one.
Well, that's precisely the point, isn't it? They've brought about this sort of invisible revolution.
Wait.
These devices are in, well, virtually every automatically controlled product and device you interact with daily. Seriously, think about it.
Okay, like what? Give me some examples.
All right. The system controlling your car's engine. Definitely. Many implantable medical devices, pacemakers, for instance.
Wow.
Your TV remote control, office machines like printers and scanners, household appliances, your washing machine, microwave oven, dishwasher.
My microwave has one.
Oh, absolutely. Power tools, even many kids' toys these days.
Huh. So when I push a button on my remote, it's actually a tiny microcontroller waking up, interpreting that signal, and sending it to the TV.
That's exactly what's happening. A dedicated little brain just for that job.
That's kind of incredible when you think about it. And the impact on the cost and size of all these products must have been just astronomical, right?
It truly was. I mean, by packing everything onto that single chip, they drastically reduced both the physical size and the manufacturing cost compared to older designs.
Hmm.
You know, the ones that relied on a separate microprocessor, separate memory chip, separate I/O controllers.
Like a whole circuit board full of stuff.
Exactly. And that reduction in size and cost, well, it made digital control of more devices and processes practical. It basically democratized computing power for everyday objects.
And now they're playing a huge role in the Internet of Things, I imagine.
Oh, absolutely. They're the quiet backbone of the IoT. They act as these incredibly economical and popular means of data collection, sensing, and actuating the physical world as edge devices.
Edge devices, meaning they're out there interacting directly with the environment.
Precisely. They're literally the eyes, ears, and hands of the Internet of Things, collecting data and making things happen based on instructions or sensor readings.
This is where it really gets, well, kind of mind-bending. Can you give us some hard numbers just to really grasp the scale of how many of these things are out there?
Okay, prepare yourself. A typical home in a developed country is likely to have only 4 general-purpose microprocessors. Think laptops, desktops.
Oh, right, the ones we actually see.
Yeah,
Yeah.
but around 3 dozen microcontrollers.
3 dozen in one house.
At least. And get this, a typical mid-range automobile has about 30 microcontrollers scattered throughout its various systems. Engine control, transmission, brakes, airbags, infotainment, door locks.
30. Okay, that's astonishing. So while my phone might have one super powerful processor, my car, or washing machine, has this hidden army of little dedicated brains.
That's a great way to put it, an entire hidden army, each doing its specific vital job.
Okay, so they're everywhere now, and they made digital control affordable and practical. But how did we actually get here? From, the earliest computers filling entire rooms to these grain-sized marvels we're talking about.
It's quite a story. And to understand the microcontroller's birth, we really need to quickly touch on the dawn of microprocessors first.
Okay, set the stage.
So there were early multi-chip microprocessors, like the four-phase systems AL1 back in 1969. Garrett Airsearch had one in 1970. But the big one was the first single-chip microprocessor, the famous Intel 4004.
Ah, yes, the 4004, 1971.
That's the one. Developed by that legendary team. Federico Fagan, Marcian Hoff, Stan Mazer, and Masatoshi Shima at Intel. A huge leap forward.
So a whole processor on one chip, that sounds like the microcontroller right there.
Right.
But it wasn't quite, was it?
Yeah. Correct. It was a massive step, but the critical limitation was that these early microprocessors, including the 4004, they required several external chips to implement a working system.
Okay, so you still needed separate chips for memory, for input output.
Exactly. Memory chips, peripheral interface chips, clock generators, the whole setup. And that meant the total system cost was still several hundred 1970s US dollars.
Which was a lot of money back then.
A huge amount. Far too expensive and complex for, say, economically putting a computer into a simple calculator or a small appliance. It just wasn't practical yet for those embedded applications.
Okay, so when did the true breakthrough happen? The computer on a chip, specifically designed for controlling everyday devices.
Well, that credit really goes to 2 engineers at Texas Instruments, Gary Boone and Michael Cochran.
Texas Instruments, okay.
They're credited with the successful creation of the first microcontroller in 1971. Their work led to the TMS-1000, which became commercially available in 1974.
The TMS-1000.
Yes. And this chip was genuinely revolutionary because it truly combined read-only memory, read-write memory, processor, and clock on one chip and was targeted specifically at embedded systems.
So that was the first real all-in-one solution.
That was it. A complete miniature brain designed from the ground up for control tasks.
A massive leap forward.
Yeah.
What was Intel's response to this? Did they jump on the microcontroller bandwagon?
They did. Partly in response to the TMS-1000, Intel developed the 8048. It started shipping commercially in 1977.
The 8048.
Yeah, and this was also very much a computer system on a chip optimized for control applications. It combined RAM and ROM with a microprocessor core, and it became incredibly successful.
How successful?
Get this, it eventually found its way into over 1 billion PC keyboards.
A billion keyboards. Just for the keyboard control.
Just for the keyboard controller. Intel's president at the time famously called it one of the most successful products in the company's history. It really cemented the idea of the microcontroller.
That's just astounding. A billion.
Wow.
Now, you mentioned memory, like ROM being on the chip. How did that on-chip memory evolve? Because early versions sound a bit inflexible, like permanent.
They certainly were initially. Early microcontrollers often used what's called mask ROM.
Mask ROM?
Yeah, where the program code was literally etched into the silicon mask during manufacturing, like physically built in.
So no changing it once it was made. At all.
Not a chance. Great for mass production if the code was perfect, but terrible for development or updates. For prototyping, they used erasable chips, EEPROMs.
EEPROM. I remember those. They had that little window, right?
That's the one, a transparent quartz window, so you could blast it with ultraviolet light to erase the memory and reprogram it.
Okay.
But these were significantly more expensive because they needed those special ceramic packages with the quartz window. There were also cheaper one-time programmable or OTP versions, basically EEPROMs without the window. You could program them once, and that was it.
So, still not ideal. You couldn't easily update the software once it was in a device, which sounds like a huge limitation for, well, almost anything complex. When did that crucial flexibility arrive, the ability to easily update the firmware?
The real game changers landed in 1993, a pivotal year.
Okay, 1993, what happened?
Well, two key things. First, Microchip introduced the PIC16C84. It was one of the very first microcontrollers to use EEPROM memory.
EEPROM, electrically erasable.
Programmable read-only memory. Exactly. This was a breakthrough because EEPROM allowed the chip to be electrically erased quickly without an expensive package.
No UV light needed.
Right. And critically, this enabled in-system programming. You could update the firmware, the software on the chip, right there on the circuit board electronically. Huge deal.
Definitely. And the second thing in 93?
That same year, Atmel introduced the first microcontroller using flash memory.
Flash memory, like in USB drives.
Sort of, yeah. Flash is essentially a highly optimized, block erasable type of EEPROM. It offered even better density and cost effectiveness. And today, because of that flexibility and cost, nearly all microcontrollers use flash memory for storing their programs.
So flash memory really unlocked their widespread adaptability. Okay, we've covered the CPU and the memory. What else is packed into these tiny chips? What kind of toolkit do they have on that single integrated circuit?
Right. Well, beyond the CPU and memory, one of the most fundamental features is what's called general purpose input-output pins, GPIO.
GPIO. Okay, I've heard that term. How do they work in, like, a real-world scenario?
Think of them as the microcontroller's direct connection points to the outside world. They're really flexible.
How so?
Well, GPIO pins can be configured by the software to be either inputs or outputs. So if your washing machine needs to know if the door is shut, a GPIO pin is configured as an input, and it reads the signal from the door switch. And when the microcontroller needs to, say, turn on an indicator LED or tell a motor controller to start spinning the drum, another GPIO pin is configured as an output to send that command signal.
Got it. Input for sensing, output for controlling.
Exactly. And many embedded systems also need to read analog signals from sensors, things like temperature or light levels or pressure, which aren't just simple on-off digital signals.
Right, like we talked about before, the analog world.
Precisely. So microcontrollers very often include analog to digital converters, or ADCs.
ADCs.
Yeah, they translate those real-world analog voltages into digital numbers that the chip's processor can actually understand and work with.
Makes sense. And do they go the other way, digital to analog?
Sometimes, yes. Some include digital to analog converters, or DACs, although they're maybe a bit less common than ADCs. DACs allow the microcontroller to output a variable analog voltage or signal, perhaps to control something very smoothly.
So they can essentially sense and act upon the physical world directly, in both digital and analog ways. What about timing? Precise control for things like, I don't know, managing an engine's fuel injection or something. That needs perfect timing.
Absolutely critical. And that's where various built-in timers come in. A very common one is the programmable interval timer, or PIT.
PIT?
Yeah, it's incredibly useful for triggering actions periodically. Like a thermostat might use a PIT to check the room temperature precisely every, say, 5 seconds.
Okay, for regular tasks.
Right. And they also often include something called a pulse width modulation block, or PWM block.
PWM. Heard of that one too. What does it do?
PW is really clever. It allows the CPU to very efficiently control things like the brightness of an LED or the speed of a DC motor or power converters. It does this by rapidly switching a digital output pin on and off. By varying the ratio of on time to off time the pulse width, you can effectively control the average power delivered.
Ah, so it simulates an analog output using just digital switching.
Exactly, and it does it very efficiently without needing a lot of CPU attention once it's set up.
Smart. And I imagine these chips often need to talk to other chips or maybe even larger computer systems as well, right?
Absolutely. Connectivity is key, especially now. So they have dedicated on-chip hardware, built-in peripherals that handle communication with other devices using standard protocols.
Like what kind of protocol?
Oh, common ones like UART for basic serial communication, like connecting to a GPS module. Then there's IPA and SPI, which are very common for talking to sensors or other chips on the same board. USB is often included now, and even Ethernet controllers for direct network connectivity on more powerful MCUs.
So they're well equipped to be part of a larger network.
Definitely. It's vital for their role in bigger systems, or of course the Internet of Things, allows them to send sensor data up to the cloud or receive commands remotely.
This all sounds quite complex, actually, with all these peripherals packed in. But we keep hearing about microcontrollers being incredibly low power. How do they manage that? How are they so efficient?
Yeah, it's a major design focus. Their architecture is heavily optimized for efficiency. For instance, some microcontrollers can operate at incredibly low clock speeds,
How low?
sometimes as low as just 4 kilohertz. That's incredibly slow compared to your PC, but it drastically reduces power consumption down to just single-digit milliwatts or even microwatts.
Microwatts. That's tiny.
It is, and what's truly impressive is their power consumption while sleeping. They often have special low-power modes where the main CPU clock is stopped or slowed way down.
Wow.
In these modes, power consumption can drop to mere nanowatts.
I know watts. Wow.
Yeah, which makes them perfectly well-suited for long-lasting battery applications. Think wireless sensors that need to run for years on a coin cell.
Okay, that makes sense. Are there architectural tricks they use too?
Yes, many use what's called a Harvard architecture.
Harvard architecture. Different from what's in my PC.
Often, yes. The architecture in your PC is typically von Neumann. Harvard architecture uses separate memory buses for instructions and data.
Separate buses. What's the benefit?
It allows the chip to fetch the next instruction from program memory at the same time it's reading or writing data from data memory. These accesses can happen concurrently, which boosts efficiency and speed for certain operations.
Ah, doing two things at once.
Essentially, yeah. Plus, their instruction sets the basic commands the CPU understands often include many instructions intended for bit manipulation.
Bit manipulation.
Yeah.
Like flipping individual bits.
Exactly. Setting, clearing, testing single bits very easily. This is super useful in control applications where you're often dealing with individual on-off signals or status flags. It helps make the control programs incredibly compact and efficient in terms of code size.
Okay, so they're highly integrated, surprisingly powerful for size, and incredibly energy efficient. But the real secret sauce, or in they're absolutely everywhere, must be their price. They've gotten ridiculously cheap, haven't they?
That's putting it mildly. It's been an absolutely dramatic price drop over the decades. The cost to manufacture them can be under US $0.10 per unit, 10 cents.
10 cents for a whole computer on a chip.
For the simpler ones, yes. To give you some concrete examples, back in 2018, the cheapest 8-bit microcontrollers were available for under US dollars and 3 cents. 3 cents.
3 cents. Good grief.
And even some quite capable 32-bit microcontrollers could be had for around US $1 for similar quantities.
$1 for a 32-bit brain.
Yeah. Even looking back a bit further, in 2012, the overall average selling price for a microcontroller was still only US dollars and 88 cents. Now, it's worth noting, just for accuracy, that between 2015 and 2018, there were actually some slight price increases, even on some of these low-cost parts. That was due to various global supply and demand factors, chip shortages starting to brew, things like that. But the overall trend has been massively downwards.
Wow, that's just astonishingly cheap. It explains how they can put them in, well, everything. And you mentioned 8-bit, 16-bit, 32-bit. Has there been a big shift in which ones are most common in the market over time?
Oh, a huge shift, a dramatic market dominance shift, actually. If you go back to, say, 2002, about 55% of all CPUs sold in the world were actually 8-bit microcontrollers and microprocessors. Billions were shipped in the years leading up to that. 8-bit was king for a long time.
Okay, so 8-bit used to rule. What happened next?
Well, capabilities increased and prices for more powerful chips came down. By 2011, 16-bit microcontrollers had actually become the largest volume category.
So a step up in power became mainstream.
Exactly. But the trend didn't stop there.
So what does the future hold? Or rather, what's the dominant force now? More powerful, more bits, I assume? 32-bit.
You assume correctly. The future is definitely 32-bit, and arguably the present is too. Industry forecasts from IC Insights, for example, predicted that by 2017, 32-bit MCUs are expected to account for 55% of microcontroller sales.
Over half the market being 32-bit. Wow, why the big shift?
It's really driven by increasing demand for higher levels of precision in embedded processing systems. Think more complex algorithms, better sensor processing, and also, crucially, the growth in connectivity using the internet.
Ah, the IoT effect again.
Exactly. Handling network stacks, security protocols, richer user interfaces that all benefits from more processing power and wider data paths. For instance, in cars, complex 32-bit MCUs are expected to account for over 25% of the processing power in vehicles, handling things like advanced driver assistance systems, infotainment, and complex engine management.
Right, makes sense. And it seems like this plummeting cost, combined with the relentless drive for integration, has enabled these things to just get smaller
Yeah,
and smaller and smaller. We're talking about like world's smallest computer territory now, aren't we?
absolutely. The miniaturization has been truly breathtaking. It's hard to even picture sometimes. On June 21st, 2018, the University of Michigan announced what they called, quite literally, the world's smallest computer.
Okay, how small are we talking?
This device is described as a 0.04 millimeter, that's cubic millimeters, 16 NW nanowatt, wireless and batteryless sensor system.
Batteryless too.
Yep. And it measures just 0.3 millimeters to a side. To give you a sense of scale, that is utterly dwarfed by a single grain of rice.
0.3 millimeters. That's basically invisible. How does it even get power or send data?
Get this. It actually receives its power and transmits its data using visible light, like a tiny microscopic solar cell and optical transmitter.
That's science fiction stuff right there. Was there another famous tiny computer around that same time that got a lot of headlines? I feel like I remember something from IBM.
Yes, you're right. Just a few months earlier, in March 2018, IBM unveiled a computer that they described as smaller than a grain of salt.
Smaller than salt. Okay.
That one, they said, packed 1 million transistors and cost less than $0.10 to manufacture. It was intended for things like logistics tracking and creating digital fingerprint applications for products.
So IBM's was tiny, but Michigan's was even tinier.
Significantly so. The University of Michigan device is actually 1/10 the size of that IBM chip. It's just a stark illustration of how minuscule computing power has become. Mind-boggling, really.
Absolutely mind-boggling. Okay, so these amazing tiny brains exist. They're cheap, they're powerful for their size. But how do engineers actually bring them to life?
Mm.
How do you program one of these things to actually do something useful, like control a microwave or read a sensor?
Right, the development process. Well, traditionally, way back, microcontrollers were originally programmed only in assembly language.
Assembly language. That sounds hard. Very low level, right?
Incredibly low level and complex, yeah. You're essentially talking directly to the chip hardware in its most basic native tongue. Very tedious, very error-prone.
Okay. I imagine things have improved since then.
Oh, thankfully, yes.
Yeah.
Immensely. Now, various high-level programming languages such as C, Python, and JavaScript are now also in common use for targeting microcontrollers and embedded systems.
C, Python, even JavaScript. That makes it much more accessible, surely.
Hugely more accessible, especially C and C++ they're very widely used. But Python, particularly MicroPython and JavaScript, are gaining traction for certain types of embedded applications, especially in the IoT space. It makes development much faster and easier for a wider range of developers.
That sounds like a huge relief for developers. What kind of specialized tools do they use when they're working with these chips? It's not like running code on your laptop, I guess.
No, it's definitely different. They often rely heavily on simulators first.
Simulators, software tools.
Exactly. Software programs that run on your development PC and let you analyze what the behavior of the microcontroller and their program should be if they were using the actual part.
Ah, so you can test the code without needing the physical chip right away.
Precisely. It's incredibly useful for debugging logic errors and analyzing problems that might be really difficult or time-consuming to reproduce on the actual physical hardware.
Okay, what else? What about when you do have the hardware?
Then a key tool is often an in-circuit emulator, or IC.
IC and circuit emulator.
Yeah. Modern microcontrollers are usually designed with special on-chip debug circuitry built right in. When you connect this circuitry to an external ICE pod or probe, usually via a standard interface like JTAG or SWD.
Okay.
This allows for debugging of the firmware in real time while it's running on the actual target chip. You can step through the code line by line, inspect variables, view the chip's internal register states, set breakpoints, all while it's running in the real circuit.
That real-time debugging sounds absolutely essential, especially for tracking down tricky hardware interaction bugs.
It really is indispensable for serious embedded development.
And what about updating the software? Can the firmware of the code on the chip be updated after the microcontroller is already built into a device?
Yeah.
Out in the field, that seems like a potential game changer for product longevity and fixing bugs.
It absolutely is, and it's very common now. This is known as firmware flexibility. Most modern microcontrollers use flash memory, as we discussed, and these are field programmable devices.
Field programmable.
Meaning they allow for a field update of the firmware or permit late factory revisions to products that have already been assembled, maybe even sold.
So you can push out updates over the internet, potentially.
Exactly. Over-the-air OTA updates are becoming standard for many connected devices. This dramatically reduces the lead time required for getting new products or features to market and allows manufacturers to fix bugs or add capabilities long after the product has shipped. It's huge.
Definitely. Are there still cases where the program is permanent, though?
Yes, for very high volume, cost-sensitive applications, sometimes mask-programmed parts are still used.
Back to the mask ROM idea.
Sort of, yeah. Here, the program code is permanently laid down during the chip's manufacturing process itself. It's the absolute cheapest way if you need, say, hundreds of thousands of identical devices, and you're certain the code won't need changing.
Yeah.
But you lose all flexibility.
Right, high risk, potentially high reward if you get it perfect.
Exactly. And one other thing, you can also sometimes get customized microcontrollers. These integrate a block of personalized digital logic alongside the standard MCU core, tailored for specific extra processing capabilities, unique peripherals, or interfaces needed for a particular application.
Okay, so lots of options for programming and updating. This all sounds incredibly efficient and predictable, which, as you said, I imagine is absolutely crucial for safety-critical systems like car brakes or medical devices. But is there a hidden challenge? Something tricky about making sure these microcontrollers react instantly when something unexpected happens?
Yes, there is, and it's a profoundly critical concept in the world of real-time embedded systems, managing interrupt latency.
Interrupt latency. Okay, break that down for us.
So while microcontrollers are designed for control and often speed, they often seek to optimize interrupt latency over raw instruction throughput. What that means is it's not just about how many millions of instructions they can process per second, but more importantly, how quickly and crucially, how predictably they can respond to an external event or signal and interrupt.
An interrupt being,
Yeah.
like a sensor suddenly detecting something important.
Exactly. A signal that says, hey, stop what you're doing right now. Something urgent needs attention.
Okay. Why does the latency, the delay in responding, matter so much? For something like an engine controller or a medical device?
Because for safety and performance in systems like engine control, anti-lock brakes, medical monitors, industrial robotics, a predictable and extremely fast response time to an event is absolutely essential.
Right.
Think about needing to fire an airbag milliseconds after a crash is detected, or adjusting fuel injection based on constantly changing engine conditions. Any unpredictable delay, even just a few microseconds or milliseconds, could have potentially severe, even catastrophic consequences. Predictability is key.
Okay, I see. So what are the hidden costs then? What actually contributes to this latency? What makes it hard to guarantee that instant, predictable response?
Well, there are a few main factors. One major one is called context switching.
Context switching.
Yeah. When an interrupt signal arrives, the processor has to immediately stop whatever task it was currently running. But before it can jump to the special code that handles the interrupt service routine, or ISR, it has to save its current state.
Save its state, like what it was working on.
Exactly.
No.
It has to save the contents of all its internal CPU registers, its program counter, status flags, basically a snapshot of its current working context. It pushes all this onto the stack memory. Then it runs the ISR. And when the ISR is finished, it has to pop all that saved state back from the stack to resume the original task exactly where it left off.
Ah, okay. And that saving and restoring takes time.
It takes time. And the more internal registers the CPU has, the more stuff there is to save and restore, and the longer this context switch takes. That directly adds to the interrupt latency.
I see. What else increases latency?
Another major factor is the existence of critical sections in the main program code.
Critical sections.
These are specific parts of the software that simply cannot be interrupted halfway through. Perhaps they're manipulating shared data that would get corrupted if accessed by an interrupt at the wrong moment, or controlling hardware in a sequence that must complete.
Okay, so the code temporarily disables interrupts.
Effectively, yes. While the processor is executing inside one of these critical sections, it will typically mask or ignore incoming interrupt requests. So if an interrupt signal arrives during a critical section, that interrupt just has to wait until the section is finished.
And that waiting adds delay.
It adds delay, increasing the worst-case latency for that interrupt and potentially blocking other, maybe even higher priority interrupts that arrive while the first one is waiting. Predictability suffers.
Right, okay. So these are real challenges for real-time control. How do microcontroller designers get around these issues? How do they ensure those lightning-fast, predictable responses when they're absolutely needed?
Designers employ a number of clever hardware and software strategies. On the hardware side, some chips use what are called shadow registers.
Shadow registers.
Yeah, basically duplicate sets of the main CPU registers that are reserved only for use by the interrupt service routines.
Ah, so when an interrupt occurs.
The ISR can just immediately start using the shadow registers without needing to save the main registers first. This drastically reduces or even eliminates the context switching overhead for simple interrupts, saving precious time.
Clever. What else?
They also design the CPU core carefully, often using short pipelines, meaning fewer instructions are in flight at once makes it quicker to stop and respond to an interrupt. Applying RIC design principles, reduced instruction set computing, which generally means simpler instructions that execute in a predictable, often single clock cycle, also helps minimize timing variations.
Simpler instructions mean more predictable timing.
Generally, yes. And finally, a really important mechanism is interrupt prioritization. Most MCUs allow different interrupt sources to be assigned different priority levels.
The urgent things get higher priority.
Exactly. A high-priority interrupt, like maybe from a safety sensor, can actually interrupt a lower-priority interrupt service routine that might already be running. This ensures that the truly time-critical tasks get the fastest possible, most predictable response, even if other, less urgent interrupts are also happening.
Okay, that makes a lot of sense. Wow. What a journey we've been on. We've really peeled back the layers on these microcontrollers, haven't we? From their humble beginnings as these complex multi-chip systems to their absolute omnipresence today as these tiny, powerful, integrated workhorses.
Quite the evolution.
Yeah. And hopefully you listening now have a much deeper understanding of these invisible computers, as we call them, that digitally control so much of our modern world, making everyday objects smarter, more efficient, and more responsive.
They truly are the unsung heroes of modern technology, aren't they? Enabling so much of the convenience and capability that we often just take for granted.
Absolutely. So here's a final thought to leave you with. As you look around your home or your office, or even just think about your car, consider where these tiny brains might show up next. As microcontrollers continue that relentless march, shrinking further, becoming even cheaper, more powerful, and integrating ever more seamlessly with connectivity for the Internet of Things. What new, maybe unexpected devices or processes do you think will become smart or digitally controlled next?
It's fascinating to speculate.
Where will these tiny, powerful brains pop up that we maybe can't even imagine today? Something to ponder, perhaps, as you interact with the increasingly intelligent world all around you.